What's going on YouTube? This is a rather lengthy 4-part series in which I attempt to repair, modify, and overhaul this 1974 Silverface twin reverb. In the last video we installed 1 ohm resistors to the cathodes of the power tubes to make measuring the current through the tubes much easier. And I presented a different method, a different equation for setting the bias. Again, it's much easier. We encountered and fixed a low volume early breakup issue. We addressed how we're going to deal with the speaker cabinet and the speaker configuration, and then we fixed a zapping sound that we were hearing. In this video, I will attempt to explain how the push-pull master volume works with the boost, and we're actually going to remove that feature and remove it completely. And in its place, we're going to add a negative feedback control, and I'm going to attempt to explain how negative feedback works as well. I think we're going to run this amplifier through an oscilloscope, looking for any other gremlins that may be hiding in there. And at that point, we're going to reassemble this amplifier and check for any other issues that may be present. And we're actually going to address a reverb issue that came up once I did reassemble the amplifier as well. Once that's repaired, we'll do a final sound check, and then that should be it for this video series. So it's been a couple days since I've worked on the amp last, but I have been able to play it. I'm happy with where I'm at right now. I think everything's repaired and it's stable at this point. I think finally I've gotten rid of the static and popping. The bias is working great. I'm able to easily set the bias in this and measure it with the 1 ohm resistors and the variable pot that was installed. And I think at this point this amp is fixed. However, I did contact the customer and just to see if he wanted it back in the current state it was in, or if we wanted to do the mod of removing that master volume switch and putting in a variable negative feedback control, and he said go for it. So we're going to push on with this mod. So we're going to be losing all this circuitry here, the master volume with the push-pull switch, and then we're going to modify some of the circuitry in here to accommodate that change in the circuit. There's a couple steps we're going to have to take to actually make this a successful mod. We're eventually going to be taking out this whole circuitry here at the push-pull master volume pot, and I think I'm going to get out the schematic to attempt to try to explain how this boost works and why it would be a good idea to get rid of it entirely. There's also some circuit changes we're going to have to do on the board here as well to get it to function properly. So let's get out schematic and go from there. Alright, so let's take a look at the vibrato channel of the amp. We've got our input signal here. It'll come over to the grid of our preamp tube. It will then go through your tone stack here, your EQs, and then it will go into the second half of the preamp tube. From there, it will come out of the plate and head up to the phase inverter, but it also splits down here out of the plate, and it follows down to our reverb section of the amplifier. From there, it's going to hit your reverb tube, and it's going to come out of the plate, and that is an further amplified signal, and it typically goes to the equivalent of a transformer that, as opposed to pushing a speaker cone, it is going to drive a reverb tank. Now, when we engage that push-pull switch, what it's actually doing is kind of coming off of this transformer and rerouting the signal not to hit, well, it's going to hit the reverb tank, but it's going to also come out and allow us to route over to the second half of our reverb recovery tube, which then gets passed along to the phase inverter, which gets fed out into the output tube section. So it's almost like the equivalent of another gain stage. So once this is engaged, we're taking that further amplified signal and feeding it back into the circuit, which gives us our boost. Alright, so the first step we're going to take to complete this mod is actually just start right around here. What we're going to look for is a green wire, a black wire that goes to the reverb tank input. And what we'd like to do is sever the connection from this green wire to the master volume switch. So what we're going to try to eliminate first is actually just this small section of the schematic right here. After the removal of this wire, we're going to have to come up here and remove this section as well. And then lastly, we'll have to actually remove the potentiometer. And so where we have that is actually over here. Here's the green wire coming out of the transformer. It's going to our reverb input connector. And what we're going to do is, it's this white wire right here. We're going to sever. If we look here, we can actually trace it up. It goes through all this mess here, but it ends up right here, this one that's kind of wrapped around this mess of wires, and it finally goes to the master volume switch. So we're going to desolder that and get rid of it. Alright, we got the white wire unsoldered from it, and what I'm going to do is just kind of fish that whole wire out of there and get it kind of over here towards the master volume pot. Alright, so now that that's out of the way, I'm going to come back down and resolder this guy here. Alright, at this point we successfully removed this section right here. This was that really long white wire, and at this point it hits the master volume switch. And then, so now we're looking for a black wire that comes and meets at a 1K resistor and a 470,000 ohm resistor to the master volume switch. You can see it here. Here's the 470K resistor and your 1000K resistor here. And here is the black wire that runs over to the master volume pot. So we're going to go ahead and desolder this guy and remove it. Alright, so at this point we've got the black wire removed from those two resistors, and then we've got the white wire removed from the input of the reverb tank. Alright, next step is to take care of this section here. We're going to be severing the connection from the master volume switch to the junction of this 1 meg ohm resistor and this 0.01 microfarad capacitor. And so we're really just severing this wire here and there. If we follow from our master volume switch, we're going to come over here, and we're actually going to find our 1 meg resistor right here, the 0.01 microfarad cap here. And so we're going to snip this shielded signal wire here, and then the ground wire that comes along with it right here on either side of that 1 meg resistor there. So just got this section of the circuit desoldered. We'll throw this guy over to the side here and move on to the next step. At this point, the signal wire's been cut, the ground's been cut, and the booster switch section of the push-pull pot has been removed. So at this point, we've severed the connections here from the master volume switch. We'll need to remove the 1 meg ohm resistor, the 0.01 microfarad capacitor, and then the 12K resistor. So these are no longer needed. I'll show you on the actual board here. Here is, underneath these wires, here's your 12K resistor, your 0.01 microfarad capacitor, and then your 1 meg ohm resistor. So we're gonna actually lose all three components. All right, at this point we've got all three components removed, the 12K, the 0.01 microfarad cap, and then I think we had the 1 meg ohm resistor there. So I've gone ahead and resoldered this connection here and this connection here. So at this point, we've cleanly removed from circuit the actual boost function of the push-pull switch. We're going to move on to actually addressing the master volume portion of this circuit as well. So we're going to follow these wires down from the master volume. We'll remove them, and then we'll make some changes onto the circuit board to accommodate functionality with the master volume actually out of circuit at that point. Let's take a quick look at how the master volume actually works in circuit, and then what we're going to have to do to change it since it's going to actually be removed. So we'll come over here. Here's the input of your guitar. It hits the grid of your first preamp tube. If you're in the normal channel, if you're in the vibrato channel, it'll just go to V2 instead of V1. So let's just use the normal channel for this example. So we come in to the normal channel with the guitar input signal, hits the grid, it gets amplified, it comes out of the plate, it hits your tone stack into the second half of V1, hits the grid, out of the plate, and then at that point it runs up here to the master volume. Let's say if your master volume is set to 10, all of the signal will then be passed over to the phase inverter, which then heads out to your output tubes to the speaker. That's all the way up. Let's say if it was at a setting of 0, then your signal would get dumped to ground. Now, if we remove the master volume potentiometer, we're actually severing the connection from the preamp tube to the phase inverter. And so what we're going to have to do is actually restore a connection. So we're coming out of the plate of V1, the second half of V1. Since this 120 picofarad and the actual potentiometer is going to be removed, we don't have a path to the next stage of our amplification. So we're going to have to create a jumper from here over to this 0.01 capacitor. Now with the jumper installed from here to here, we've got no way to vary the signal strength. And so that would be in effect like a master volume would be set at 10 at all times. So let's find that connection. We're looking for the two 220K resistors. That is, this wire goes up to the master volume. Here's the two 220K resistors. and that goes to, let's see here, that goes over to the 0.01 microfarad cap. Here's the other wire that goes to the master volume. Here's the 0.01 cap. And so we are going to run a wire from here to here, and then remove this whole circuitry. So we'll make those changes real quick, and we'll check back in. So we now have both wires released from the circuit here. There was a signal wire here, and then a connection to ground up here. I did have to take off as well. And at this point, we can get rid of this whole mess and remove the actual pot for the master volume. Next steps will be to run a jumper from our 0.01 microfarad cap up here to our intersection of the two 220K resistors. So we'll do that next. So at this point, we now have our jumper from our resistors to our capacitor, and we've successfully removed the entire push-pull master volume switch. So we've gotten rid of this whole section here. If you're wondering where the 120 picofarad capacitor is, it is actually that little guy right on the actual potentiometer. So now that all that's been removed and we have our jumper from here to here, this should be as if it is as if the master volume was still there, but at a setting of 10 permanently. So I think at this point we're going to power it back up and do a sound check just to make sure everything is working as normal. All right, I've got everything hooked back up. We've got sound, so we're looking pretty good. I think we're at about 2.5 at this point, and man, this thing is blisteringly loud. So we'll do a little sound check. Everything's sounding great, so I think at this point we'll move on to the negative feedback controls. I'll try to explain what negative feedback is, how it works, and how we could potentially make a variable control actually useful. Before we start getting into what negative feedback is, what the original intent of it was, and how it can be useful to us, we need to talk a little bit about what phase is. So I've got here kind of just a representation of what would be an audio signal. Let's say that as the signal comes in, and let's say it goes up, let's say that would be an increase, a positive increase, and then as the signal goes down, let's say that would be a negative reduction of the signal, and it just goes back and forth like that. So let's say I have a signal doing its thing, and let's say I throw another signal on top of it. We've got this first increase here, and let's say that'd be like a +5, for example. This would be a +5 at the same time, and then let's say -5, and you can see they're doing the exact same thing at the same time. These two signals are what's called in phase. Now let's say we flip the phase of the second signal. So at the first instance here of our waveform, let's say for sake of argument, we're at +5 here. Now at the same time, signal 2 is at a -5. So in theory, they cancel each other out. And this occurs at every instance of the waveform here. Alright, so we have a schematic. We're going to go back to the Fender Champ. Now that we've discussed a little bit about phase, we'll show you where the negative feedback loop is located in the Fender Champ, and how it was designed and the original intent for the negative feedback loop. So here's our negative feedback loop coming out of the output transformer. It comes, let's see here, so we've got our guitar signal, hits the grid, your master volume out of the plate, then it hits the master volume, hits the grid, the plate again to your output tube, hits the output transformer, and out of that, here's our negative feedback loop. It's coming out of the output transformer. It comes over, hits this 22K resistor, and then it gets fed back into the preamp tube here at the cathode. Now the way that this works is that the signal coming out of this output transformer gets fed back into a previous stage of the amplifier. However, this output signal is out of phase from this signal. The original intent of your negative feedback loop was to reduce distortion in the amp and actually reduce gain as well. Now the effects of a high amount of negative feedback, and that would be less resistance here, would be a decrease in overall gain and almost a flattening of your tone. Now the opposite, the effects of less negative feedback, which would equate to more resistance, gives us an increase in gain as well. Now that's a pretty narrow view and way to think about it. It actually affects more than gain alone. It affects your overall tone. It's almost, think of it as a flattening of the tone with a high amount of negative feedback and a more lively amp with less feedback. And who's to say that one is more desirable than the other? I think it's a pretty unique control to have on an amplifier. And so what we're going to do is we are actually going to, let me pull out the Fender Twin schematic here. Here's our negative feedback loop going into the phase inverter from the output tube. So what we're going to do is actually find a way to go below this resistance value and then way above it to give us kind of a wider range of control with this negative feedback circuit. So what we're going to do is we're going to, so that's an 820 ohm resistor. I think it's right here next to the coupling cap. We're coming out of the output transformer to the output jacks, and then we're running from the output jacks up to this 820 ohm resistor, and here's our output transformer hitting our speaker jacks, and then that white wire is heading to this 820 ohm resistor. So what we'll do to give it more negative feedback is we'll reduce this resistor to maybe half, maybe around 400 ohms, and then we're going to install a potentiometer as well, and that will allow us to go way above this resistance value to give us even less negative feedback. And I think having that ability to control that might open up the possible sounds that we can get from this amp. So the way the negative feedback circuit actually works is that, let's say for this example, two out of phase signals cancel each other out. They would suppress each other, and you would theoretically not get much sound out at all. Let's say this is the negative feedback signal being sent in on top of your original signal. What we can do is vary this amount of out of phase signal that gets injected into the original signal. So let's say, for example, this first waveform has a value of +5, and let's say here comes your negative feedback signal, and let's say we've got it set at a setting that would give us -2. So the total output of this first waveform, what's the math on that? So we got 5 minus 2. Your total output would be 3 from your original signal. And we can vary that amount. We can make it no negative feedback, which would allow us to maintain all of the original signal, or we could give it maximum negative feedback, which would suppress that original signal. All right, so we've got our negative feedback loop coming out of the output transformer. It's hitting the output jacks. It hits this wire right here. It goes up to our 820 ohm resistor to the actual phase inverter right here. And so what we're going to actually do is we're going to keep this wire coming from the output transformer. We're going to replace this resistor. But what we have to do is wire in a potentiometer in series after this resistor. And then after the pot, we're going to come into here, which will then go to the phase inverter to the output tubes. I think the best way to do this is to, once we remove this resistor and replace it with a lower value, it normally ties into here, which goes into our phase inverter. We're going to move this connection, I think, to this empty connection here. Out of there, we'll come out and then we'll run a wire over to the pot. Once it hits that pot, it'll come back out and then hit our phase inverter. And then that should take care of a variable negative feedback control. And I think to complete this mod, I think I'm actually going to use the original wires that were intended for the push-pull master volume switch, just to keep everything kind of vintage and looking the part. I don't want to see any, really bright orange wires in there or anything like that. I kind of like the look of the old vintage stuff, so we're gonna try to keep with it. So we've got the new, I think we did a 470 ohm resistor coming off of the negative feedback. This is going out to this wire here, which will be routed over here to the potentiometer. Once it gets routed back, it'll come through this black wire that will feed our phase inverter out to the output tube. So our next steps will be to actually put the potentiometer in series with the 470 ohm resistor. So what I have on hand for the potentiometer we're going to use is a audio taper 10,000 K pot. I didn't have any linear pots available to me at the time, so this is what I've got. So this is what I'm going to use. So a quick note on how pots work. Basically, you've got 3 connections here. The middle connection is called the wiper. So what we can do is actually inject a signal into here. Now what this is a pot in the orientation like this at the moment. And so what we can do is we can inject a signal here. Now that signal will travel along a resistive strip, and that wiper follows along that strip. And so if we've got a signal coming in here, and let's say that the wiper was set right about here, it wouldn't see that much resistance to get out of that wiper. Now let's say we turn this wiper, and now as opposed to this wiper being right here, let's say it's all the way over here. So now that signal, as it enters, it will have to travel a much greater distance along that resistive strip, thus making the resistance greater. So this wiper would be over here, that signal would have to travel much further along that strip. And so that's kind of how a variable resistor in the form of a pot would work. Now there's a couple different ways we can hook this up depending on how we think about what we're trying to do. In my opinion, for the customer, I think as we increase the dial on the pot, I'd like to have him mentally be in a state where that equates to more negative feedback. Now, in order to achieve more negative feedback, we need to do the opposite, which is reduce the resistance of that negative feedback signal to the phase inverter. So what I propose we do is come in to this, to the right lug, and if this pot was at a setting of 10, it would be, since the orientation right now is backwards, a setting of 10 would place this wiper right here, which would equate to close to 0 ohms of resistance. Since we need less resistance to achieve more negative feedback, I believe that will work for our purposes. Now let's say I came in from the other side. A setting of 10 would place this wiper over here, and that would provide the most amount of resistance. So a setting of 10 would result in less negative feedback. Almost counterintuitive, since turning up a pot on the front of a amplifier usually results in more of something. So I'd like to continue that train of thought, which provides more negative feedback. But in actuality, what's happening is that we're suppressing the output signal. To demonstrate this, I've got it wired how I propose. So this would be the equivalent of injecting my signal on the right side. A setting of 0 would place this wiper all the way over here. So we're connected, we're coming in here and we're going out here. And so with this wiper all the way down to 0, it's placing that wiper all the way over here. So the signal sees the resistance value of this entire strip. The orientation is flipped, but if we were looking from the back of the pot, we're on the right side, and the middle coming out of the wiper. So as you can see, I've got my meter set in ohms. This is a 10K pot, so we're reading 9.2 with the volume pot, or the pot all the way down. So with the pot all the way down, it sees the most amount of resistance, thus suppressing the signal. Now as I turn this pot up, you can see that the resistance value is decreasing. So as I turn this up, in the case of the negative feedback, it is allowing more out of phase signal to hit the phase inverter. this would result in the pot being set to 10 with almost no resistance, providing the most amount of negative feedback. So once this gets installed, we can now go below the original resistance value of the negative feedback, which I think was in the 800s. We can now go below that value with our 470 ohm resistor, and then with the addition of this pot, we can go way above it as well. So we've got a good margin to play with at this point. All right, so the pot's in. We got the 470 ohm resistor, the white wire. We follow it up to the right side. It comes out of the wiper to the black wire, and it hits the phase inverter. So we now should hopefully have a working negative feedback control. All right, so we'll do a little sound test. I'm in channel 2. The Verado channel, we're at around 2.5. I've got the amp set with the most amount of negative feedback, and that would be the least amount of resistance. So we're at 470 ohms. Do a little sound check. So at this point, it sounds very similar to the unmodified version of this. I can actually turn it down a little bit to kind of try to simulate 870 ohms. And then you can see there's not that much change. But if I reduce the amount of negative feedback, it does change drastically. I'll go back to no negative feedback, or I'm sorry, the most amount of negative feedback. We'll switch it to less negative feedback. I'm hearing a huge difference, like I said, with more negative feedback. It kind of squashes the tone a little bit. It kind of makes that frequency response much more linear. If we reduce the amount of negative feedback, it kind of allows this amp, in my opinion, to breathe a little bit more. So here's no negative feedback again. I'm sorry, I keep getting that backwards. Here's the most amount of negative feedback. So the pot's at 10. Sounded pretty good. I mean, it sounds like a normal twin. If we back that off just a little bit. It does get a little bit brighter. It gets a little bit more bassy. I would say somewhere in between the stock value and where I had it. I wouldn't run this wide open either way. So, but I'm definitely liking it. It's also worth noting, again, I'm wishing that I used a linear pot for this. The reason being that the audio taper kind of doesn't do much from 1 to 5, and then from 5 to 10, it's the majority of the resistance. So, for example, we're at all the way up right now, so that's the most amount of negative feedback. So the lowest amount of resistance. I'm going to just strum some open strings, and I'm going to turn it, and hopefully you guys can see how much I'm turning this pot, and you can see that once I turn it slightly, there's a huge effect, and then after that, not much happens from 6 down to 1. So here's an example. So right now it's the least amount of resistance, so the pot is all the way up. So I'm going to strum, and then I'll turn. I don't know if you can hear that. That small amount does a lot. And then from here, you can hear not much is different. So really a little amount goes a long way. So that's the downfall of using that audio pot. But I got a feeling once I present this back to the customer, I'm thinking he's gonna like it, and he's a pretty laid back guy, so I think I might end up seeing this amplifier again to do some more mods to it. So if that does turn out, I think I will replace that in the future with a linear taper pot. It just makes the sweep a lot more even, so you've got more fine tuning abilities with a linear taper pot for this application. So usually the audio tapers are used on the master volume control and stuff like that. So I think at this point I'm happy with where I'm at. I know I've said that in the past and have stumbled upon something else that needed to be fixed, but it is what it is. But I am happy right now, so I think we're running into the last final steps of things to do that would equate to a cleanup on this, and like I said, we'll probably end up doing just cleaning the connections, stuff like that. I do think that I'm going to run an oscilloscope through it just to take a look at it, poke around a little bit, see if I see any loose connections, and then past that, I think this thing's ready for reassembly and final delivery. Now that the amp's been repaired, overhauled, and modified, I'd like to run an oscilloscope through it to take a look at the waveform, just to see if there's any issues still present before I begin reassembly. I'll kind of briefly take you through the things that are needed in conjunction with the oscilloscope to actually make this process work, and then we'll talk about some safety issues as well. The first thing I'd like to talk about is our signal generator. This is what's actually responsible for producing the waveform that we're going to be monitoring on the oscilloscope. The signal flow basically originates at this audio generator. It gets fed over to the amp, and the components modify it, and then we'll observe actually the waveform, what it looks like here, to see if there's any issues present. Before we begin, there is a necessary piece of equipment that we're going to need. It is this guy right here. It is an isolation transformer. There's a wide range of isolation transformers available in the market. What we're looking for is a tech grade isolation transformer. You can buy medical grade, consumer grade, etc. Most isolation transformers are not tech grade. In a nutshell, what a tech grade transformer is the secondary side of this transformer is not connected to ground. When I bought this isolation transformer, it was, and so you can actually modify these transformers to make it tech grade. That's what I've done here. This has been modified. I'm actually not going to go into how to modify this. There's plenty of videos online that will show you how to do that. It is imperative that you use one of these in conjunction with your oscilloscope for your safety. The order in which we're going to hook all this equipment up is we're going to take the plug from the amplifier. We're going to plug it into our current limiter. It's going to come from the current limiter. We're going to put a 3 to 2 prong adapter on the end of the current limiter plug. That 2 plug adapter from the current limiter gets plugged into our modified isolation transformer, and I've got that isolation transformer plugged in here. When you're working with this configuration, no exceptions should be made. We should come out of the amplifier to a current limiter, 3 to 2 prong adapter, and to a tech grade isolation transformer to the wall. If you do not adhere to this set of rules, you could fry your scope, the components in your amplifier, or you could seriously injure yourself. Alright, so let's talk about how to actually hook all this up. We'll start with the signal generator. What we'll do is we'll come out of the signal generator. This is a cable, just a shielded cable that I made from an old guitar cord that goes to the connection of the signal generator. That terminates to the other end of this 1/4-inch cable, in which will go to the input of our amplifier. At that point, I would consider not hooking a speaker up to the amplifier, because it is going to be amplifying the signal that's produced from this audio generator. So what we'll do is we'll actually use this dummy load that we've got here. Again, it simulates the impedance load of a speaker. By using this dummy load, we will not have to listen to the audio that's generated by the signal generator, and I assure you it will get very, very loud, especially if we turn up the controls. So when we plug into this dummy load, obviously we'll not hear that. So we'll go ahead and plug this guy in. This oscilloscope happens to have 2 channels, so what I'm going to do is take channel 1, and I'm going to connect to the grid of V1, which is the first component that sees the actual input from our signal generator. So for this first tube, that will be pin 2. So we've got our oscilloscope probe hooked to pin 2 of V1, and then to chassis ground. Before we start turning things on, we'll set our the frequency to what we're looking for. We're going to use here 10 times 100 would give us 1,000 hertz, and down here your waveform, we're going to use not the square wave, but our sine wave. And at that point, we can go ahead and turn it on. At this point, we can actually see the signal going through the amp that's originating from our signal generator. I'd like to note that the amp is still off at this point, but as you remember, we'll come over here from our signal generator, which actually just goes to the grid. So nothing's actually been processed in that signal. We're just reading the source signal at this point. We've got what we would expect, which is a really nice smooth signal. We can take next the second channel from our oscilloscope, and we can actually hit the next tube in the signal chain here. We'll go to let's say the grid of one of the grids in the phase inverters. Alright, that's hooked up. I actually got it hooked up to one of the resistors, but as you can see, that resistor comes down here to pin 2 of the phase inverter tube. We'll go ahead and turn on our isolation transformer. The amp is off at this point. We'll flip the power and allow it to warm up. We'll go ahead and flip the standby. We do have it coming, that signal coming into channel 1, I think the volume is at about 3, and we're observing the next stage, the input of the next stage of the amplifier. And this is our signal. You can see it's much stronger than the original signal. Since this is on channel 2, I can actually flip back to channel 1, and we can see how much amplification we're actually achieving. So you can see how much bigger that signal is. I can actually overlay them so we can see a direct comparison of our input signal to our amplified signal. So this is observing the initial source frequency, and then if I combine those two channels, you can actually see the amount of amplification that has taken place. I'm actually going to turn the volume up and down on channel 1, and you can see the effect that the volume has in amplification as I cycle through this pot. Now at this point we've observed the input source frequency, but what I'd like to do next is run the signal through the entire amp, and then take a look at it directly from the output. So I have the positive probe of the oscilloscope connected to the output jack of the amplifier, grounded to chassis. We come over here and we'll take a look at what our processed signal looks like. So this is hitting most of the tubes, going through all the circuitry inside, and we're looking for it to be very smooth and clean at this point. And we can compare that to the input signal from the audio generator. We can see that it resembles it quite well. So at this point we've got a very clean signal going through the amplifier, or being put out from the amplifier rather. But if you're ever curious, what we could do is actually turn this amp up to the point of distortion, and we can actually see what that looks like. Okay, so I think I'm at a setting of about 3 on channel 1 here. What we can do is we can actually turn this up, and you can start to see right there we're starting to hit clipping. We can turn this up to the point where those top and bottom edges start to square off, and that's actually what a distorted signal looks like. Alright, so the next thing I'm going to do is a tap test. I've got the signal going through channel 1 at the moment, and all I'm going to do is start poking around on components on the eyelet board, and I'm going to try to poke at all these connections and look for any variation there on the oscilloscope. And so far what I'm seeing is pretty good. It's actually pretty rock solid. I'm actually surprised. But usually we'll go through this, and if you see any kind of bouncing around, that may indicate a loose connection, or something that you may need to reflow. And I'm always going to do this with a probe, a non-conductive probe, because you don't want to poke around in here with a metal screwdriver. You'll get zapped that way. So then I'm going to repeat this process on channel 2 as well, just to make sure everything's looking good. Alright, I'm in channel 2, just poking around, especially V2, and I'm pretty happy with this. Just to give you kind of a demonstration, it's really kind of at random. You just kind of want to go through here and poke at these connections and just to make sure that nothing's kind of running loose, and you just observe the oscilloscope. And like I said, if you see some squirreliness on the screen, just find out which connection it is, and reflow that solder. And I couldn't resist, if you've ever wondered what chords actually look like, here's a G chord, and a D chord, A chord, that one's kind of cool, C major, let's do an F minor, see if they look any different. Of course, everybody's favorite minor chord, A minor. Let's do E major 9. It's power chords. Higher ones. That one's cool. It's a high G. Vibrato. Sorry, I couldn't resist. And we'll do some lead work. So the lower notes, giving off those huge waveforms there, huge transients. And those high notes giving off those real small ones. Well, dare I say that this amp repair is complete. So I think we're going to just move forward with reassembly, and we'll do a final sound test for that. But I think everything's looking good. So the amp's finally back together. I think at this point the only thing I've got left to do is to solder the speaker cables back into the speaker terminals, just to make sure that there's a good connection moving forward. Alright, so I got the speaker wire soldered into the speaker terminals, and the tubes are reinstalled. So I think at this point we'll do one final sound test, and that should wrap up this video series. I got the amp finally put back together. Everything seems to be working flawlessly, except for the reverb. Let me see if I can give you an example of what's going on. If I dime the reverb, let's take away some negative feedback. We can get some internal feedback happening. After doing a little bit of research, let's see if I can get this reverb start feedbacking again. I can actually just reach in here and touch the reverb tank, and it goes away. If I let go, it comes back. And all I'm doing is dampening the reverb tank and so I'm kind of isolating it a little bit more from the cabinet. So I think the problem's originating here. So what I'll try to do is back off these screws and maybe see if I can find a way to further dampen the reverb tank. So after loosening the screws a little bit to the bag that secures the reverb tank to the chassis, it seemed to not take care of the feedback issue. So we're going to take it out and see if we can't find any issues. So I got the reverb tank out of the bag. We've got kind of a foam rubber strip here in an effort to isolate the reverb tank further from the cabinet, and then we got a similar attempt here with some cardboard and looks like some strips of wood to try to elevate it a little bit. So what I'm going to do is take off this cardboard strip and to see what these springs are looking like. Well, I think I found a problem here. I was not only getting feedback, but a really kind of distorted signal from the reverb tank. So this is definitely no good. So I'm going to try to see if I can reattach that spring over here to see if that will clear it all up. Well, I've got a little bit of bad news. We know what's wrong with this. Let's say this spring here connects to that little guy there. Same thing on this end, little guy right there. Here's the other end of what I have to hook that spring to. Unfortunately, this side doesn't have that connection. It is all the way over here. It is broken off, unfortunately. So I think we're going to have to get a new reverb tank. So rather than try to fiddle with this and resolder that core where the spring connects to, I know it can be done. At this point, I'm just not wanting to fool with it since these things are so readily available and cheap online. I think with shipping and everything, you might be looking at $35. So I'm going to go ahead and order a new one and throw that one in to replace this broken one. So it's been a couple days since we left off. The replacement reverb tank finally came in. It is an Accutronics 4AB3C1B, and I'll quickly show you what that numbering scheme is referring to. So if you go to Accutronics website, they've got kind of a legend that explains what all those numbers mean. So let's run through this real quick. It's a type 4 reverb. Our first digit is A, or our first digit is 4. Our second digit is A, so input impedance is 8 ohms. Digit 3 is B, so it's 2250 ohm output. 3 is our next digit, so it's a long decay time. C is our fifth digit, so input insulated, output grounded. 1 is our next digit, and then B is our final, so horizontal open side down. That's kind of how the numbering system works. So the original had this piece of cardboard with 2 wooden strips. I think that's a good idea, so I think I'm going to attach this to this cardboard section here. This did have a piece of foam with it that was inserted in here to keep everything from banging around during shipping. I actually might cut this in half and then kind of place a section here and then another section here when I put it into the bag to try to isolate this reverb tank even further from the chassis. So I've got the reverb tank installed back in the chassis inside the bag. I'm going to bring the reverb up to 10 to see if I get any of that feedback. Right now it's holding strong. I did put it in there with just the reverb tank, and it did give me the feedback. But I did, once I installed it back into the bag, it seemed to have taken care of it. I think I may experiment a little bit with those pieces of foam, wherever they may be. I might throw those underneath there. So as you can see, I've got just a couple of those foam pieces kind of mounted on underneath the bag here. And I think I'm going to experiment and just try to screw that bag down with that foam pieces underneath it to kind of act as a shock mount to see if we can't reduce that feedback even more if it needs it. Just got everything put back together. Reverb tank is back in. I did put the small pieces of foam under them, and everything seems to be holding stable. Everything's assembled once again finally in its entirety. We're going to do one final sound test on it. We're over here in channel 1 of the normal channel. Volume's about 2.5. Everything's at unity as far as the EQs and stuff. I don't have any reverb at this time. Let's do the treble. Let's max that out. Oh yeah. Let's do the middle. Do a cut. Alright, that's working. We'll do the bass. You guys probably won't hear this on your phones. Bass is maxed out. And we'll cut the bass. Oh yeah. We'll put everything kind of back at unity. We'll turn off the bright switch. Kick it back on. That's working correctly. Go over to the second input. That's working. We'll give it a little bit of reverb. Got just a little bit there. Come over to the vibrato channel, turn the volume down. We're on, we'll do 2 on the volume. Everything's at unity on the EQs. Everything sounded pretty good. We'll give it a little bit more reverb. Turn that reverb down. Alright, we'll cut the treble. It's working. Middle. Bass. Reverb's working. I've got the foot switch hooked up, so we'll hit the vibrato. Speed. So everything's working correctly. Let's do intensity. Turn that vibrato off there. Then we got our negative feedback control. I've got it set at 10, so that is the most amount of negative feedback. We'll bring it off just a little bit. And again, it's you'd have to be in the room to really, I think, hear the difference. It's almost like you've taken a blanket off of the speakers, so a lot of those treble frequencies come through. The bass is a little bit more punchy. Again, it's more alive is the best way that I can describe it. Either that or it's angrier. So that's working pretty well. Turn the negative feedback up. Just a nicer amp, and then we'll make it mad. So I think finally we're at a good stopping point. I think this amp's ready to go. Well, if you guys have stuck around this long, again, I sincerely appreciate it. I figured I'd just play a little bit to let you guys hear how the final product sounds. So I've got it on about 2.5. Again, this thing's super loud. I've got the negative feedback turned down a little bit. It might be at 9, but again, that audio taper, a lot happens in that last little bit there, so I got a decent amount of negative feedback rolled off, but it's really, really chiming, and I'm loving it. Sounds really, really pretty. And then I'm kind of a blues player at heart. It's got that real nice Stevie kind of hit to it. And I've got a Seriatone Centura pedal just for fun. I'm going to click on to give it a little bit of dirt. And so here's without. A little bit with it. It's got a lot of that really nice bite to it. Thanks for watching, guys. If you've made it to the end of this 4-part series, I sincerely appreciate it. Hopefully the information that was presented was of interest and helped some of you in some way. Videos like these posted by other users has helped me beyond measure in the past few years, and my thanks to them. And so hopefully this video series may have the same value to someone out there. So thanks again, and I hope to see you in future videos.